Okay? Let me summarize the question for you. There is a private values first price sealed bid auction. First price sealed bid auction. Private values first price sealed bid auction. There are two bidders, n is equal to 2 bidders. The valuations V1 and V2 are drawn from a distribution 0 and 1. Okay? I am asked to assume this. I am asked to assume that bidder 2 is using a bidding rule which requires him to bid the square root of his valuation. I am asked to assume this. Bidder 2 is using a bidding rule which requires him to bid the square root of his valuation. And I am asked to show that given that bidder 2 is using this rule, given this, the optimal response of bidder 1 to this strategy is to bid, I am asked to show this. My best response to B2 is equal to root B2. B1's best response is to bid 2/3 of his valuation. Okay? If bidder 2 is doing this, this is my best response to that bidding. I am asked to show this. How do I go about it? Pretty simple. I know that bidder 2 is doing this. And I want to find out, given bidder 2 is doing this, what is my best bid? What is my best bidding strategy? I recall that whenever I make a bid, I assume that I am going to hit a probability node, and at that probability node, two things might happen. I might win the auction, or I might lose the auction. Two things might happen. If I win the auction, my payoff will be V1 minus B1. It's the first price sealed bid auction. Whatever I bid, I must pay. If I lose the auction, my payoff will be 0. Therefore, the expected payoff to me being bidder 1, of my bidding B1 and the other guy bidding B2 is simply the probability that I win with a bid of B1 times my payoff from winning, which is B1 minus B1, plus probability I lose times 0, which is 0. Okay? Probability win, the only condition I will win in, the only condition under which I will win is if my bid is higher than the other guy's bid. No other condition. V1 minus V1. And please notice, ladies and gentlemen, that the reason why I am doing this, I am getting an expression like this, is because I want to differentiate this expression later with respect to V1, set it equal to 0 and solve for V1 star. That's what I am doing. And once you notice that your next step has to be to get this into the form of an expression, some expression that can be differentiated. As it is, I can't differentiate this. I need an expression that can be differentiated. How do I do that? V2 is here. If I am going to use an expression, this is the probability value, I can only find it from the distribution. So somehow I have to get a V inside here. Somehow I have to get a V inside here. How do I do that? I substitute bidder 2's bid with whatever I believe that he is bidding. What do I think he is bidding? He is bidding square root of his valuation. So follows that P V1 greater than root V2. I know this. V1 minus V1. Questions? This is an important step. Okay, this is an important step in deriving the optimal bid. Then, still not good enough because I have to express this inequality in terms of V, because the distribution is in terms of V. So P V2 less than V1 square. V1 minus V1. Okay? Alright, got it. V2. What is the probability? I am asking you here. What is the probability that a randomly drawn valuation will be less than V1 square? The answer to it will always be found from your distribution. Randomly assume some V1 square and ask yourself, what is the probability that another valuation, which I draw randomly from this population, will lie in this region? The answer is the ratio of this line segment over the ratio of this line segment. That gives you the probability. Okay, what is the length of this line segment? V1 squared minus 0, which is V1 squared. What is the length of this line segment? 1 minus 0, which is 1. Therefore, the ratio of this line segment to this line segment is V1 squared, which is the probability that this will happen. which is the probability that this will happen, that you will win. Therefore, I get b1 squared, b1 minus b1. You notice what I have done? I have converted my expected payoff function into something that can now be differentiated. That was what I was trying to do anyway. Yeah, I have got it into the form of something I can differentiate. Okay? Once I notice this, I notice that my problem really is to maximize this with respect to b1, maximize this with respect to b1, which is the same thing as maximizing this with respect to b1. Same thing. Differentiate. Here I am going take the first derivative of this with respect to b1, product rule 2b1, b1 minus b1 chain rule minus 1 plus b1 minus b1. What did I do? No minus 1. I held this constant, I differentiated this. So b1 minus b1, 2b1. Then I will hold the other guy constant, b1 squared, differentiate this with respect to b1, I'll get minus 1. This is my first derivative. My first order condition is to set it equal to 0. Now I'll solve for b1. 2b1 b1, I'm expanding, minus 2b1 squared minus b1 squared is equal to 0. Therefore, you get 2b1 b1 is equal to 3b1 squared. Therefore, you get, got it, b1 is equal to 2/3 b1. Yeah, that's what I'm asked to show. Bidder 1's optimal response, bidder 1's best choice of bidding rule, given that bidder 2 is doing this, is 2/3 b1. Clear, ladies and gentlemen? Okay? Okay. The next part of the question asks me this. This is relatively simple. I'm just doing it so that you get a logic of the maximization process. The next part of the question asks me this. Do these strategies form a Nash equilibrium? Again, translate the question, the English question, into some mathematics. I am asking you, if bidder 1 bids 2/3 b1 and bidder 2 bids square root of b2, do these bidding strategies constitute a Nash equilibrium? Again, they would constitute a Nash equilibrium if this is bidder 1's best response to this. In other words, given that bidder 2 is doing this, does bidder 1 have any incentive to deviate from here or not? Does he? The answer is no. I have just derived, given that bidder 2 is doing this, this is bidder 1's best response. Therefore, he doesn't. But that is not sufficient to show that this pair of bidding strategies is a Nash equilibrium. What must you do? You must now hold bidder 1. Given bidder 1 is doing this, does it follow that this is bidder 2's best response? That's what I mean. In other words, I will, in the same way as before, get an expected payoff function for bidder 2 in terms of what bidder 1 is bidding and what bidder 2 is bidding. I'll get this. Okay? And once I get this, I'm not going to do this again, okay? You know how to get this. Exactly in the same way as how I got this. Now I'm solving the problem from bidder 2's point of view. Okay? Okay, I'll get this. Once I get this, then I will differentiate expected payoff of bidder 2 with respect to B1 or B2? B2. This is payoff of bidder 2. I'm trying to figure out what is the optimal value of B2. Notice, in this part, in this expected payoff function, you would have already substituted this in. Okay? You would have already substituted it. Get it? Get an expression here. This expression will be, I guarantee you this, an expression that will contain a B2 and a B2. Set it equal to 0, get B2 star as a function of B2. Okay? That's what we'll do. And see whether that is equal to square root B2 or not. If it is, then follows that bidder 2's best response to that strategy of bidder 1 is also to bid square root B2. Then it is a Nash equilibrium pair of strategies. Even what one bidder is doing, the other bidder has no incentive to change to another strategy. But if it is not square root of B2, this function is not square root of B2, then is this a Nash equilibrium pair of strategies? No, that's good. is not an attribute. Questions, guys?